Java allows you to operate in a world of high-level abstractions, objects, classes, and methods. But beneath that clean, elegant syntax lies the cold, physical reality of your CPU and system RAM. The Java virtual machine acts as the primary translation layer, mapping those abstract instructions onto physical hardware. To the underlying operating system, the JVM is a rigid physical memory architecture governed by hard, unforgiving boundaries. Navigating the specific resource limits and partitioning rules of this runtime environment is what enables an engineer to build systems that scale. Garbage collection pauses and algorithmic slowdowns occur as a direct result of data crossing these physical memory partitions inefficiently. When code pushes beyond these hard limits, the JVM stops the application entirely, resulting in an out-of-memory error or a stack overflow error. Designing high-performance Java requires tracking exactly where every byte lands inside this memory blueprint as the code executes. The process begins with a finite block of system RAM allocated to the JVM, ready to be partitioned. The moment an application spawns a new thread, the JVM carves out an isolated partition exclusively for its private workspace, the stack. When that thread invokes a method, a dedicated stack frame drops into this space to manage execution. This frame is strictly for local primitive variables, like integers and characters, and the incoming parameters required for that specific method. As the thread calls more methods, new frames stack on top in a last-in, first-out sequence. The instant a method finishes, its entire frame is erased from the stack, immediately freeing that memory. Because of this deterministic clearing, the stack functions without any need for background garbage collection. However, this speed comes with a physical constraint. The stack is usually capped at a default of 1 megabyte per thread. A recursive function without a proper exit condition will pile frames until they hit the ceiling of this fixed vertical space, triggering a stack overflow error. Engineers control the physical size of this partition using the -SS tuning flag at startup. The stack architecture trades massive storage capacity for extreme execution speed and inherent memory safety. Applications processing complex data require a shared warehouse outside of these isolated thread stacks. This is the heap. When the calculate method instantiates a complex object, the memory allocation splits. A lightweight reference variable stays in the local stack frame, while the heavy payload materializes in the heap. This reference serves as the physical bridge between domains. This bifurcation governs Java's pass-by-value rule. When passing objects between methods, you copy the value of the reference address instead of moving the payload itself. If you assign that reference to a second variable, the JVM creates a second tether pointing to the exact same object in the heap. When the first connection is severed, the object remains in the heap as long as a second tether holds it in place. This bridge logic is the root cause of Java memory leaks. Static collections and unevicted caches act as permanent tethers. They prevent the JVM from reclaiming space because they maintain a valid physical path to objects long after they are no longer needed. An object in the heap only survives as long as an unbroken bridge connects it back to an active thread. The heap uses a highly organized internal hierarchy to manage these objects. This structure is governed by the weak generational hypothesis. Analysis of object lifecycles shows that the vast majority of these objects die almost immediately after their initial creation. To optimize for this, the heap is subdivided into two primary territories, the young generation and the old generation. All new objects materialize inside the Eden subdivision of the young generation. When Eden fills, the JVM triggers a minor garbage collection. Surviving objects are pushed into a survivor space while the rest are cleared. After surviving multiple collection cycles, an object is promoted across the border into the old generation. Eligibility for collection is determined by GC roots, starting points like active local variables or static references. The garbage collector traces these paths. Any object without a reachable path to a root is flagged for destruction. Algorithms like G1GC and ZGC manage these sweeps concurrently to prevent the application from pausing for long periods during cleanup. The garbage collection system functions as a physically partitioned pipeline determined by the real-world survival statistics of your data. Beyond threads and data, the JVM requires a space to store the actual class definitions and bytecode rules. This information lives in a dedicated storage area called metaspace, which holds class metadata, static variables, and constant pools. Metaspace allocates directly from native OS memory, separate from the limit set for the heap. Large frameworks that generate classes dynamically can exhaust this specific native memory, causing a metaspace out-of-memory error, even when the heap has plenty of room. This shared heap architecture also introduces the challenge of concurrency. Because multiple thread stacks connect to the same heap space, independent threads may attempt to update the same variable at once. The Java memory model provides the rules for these interactions. The volatile keyword establishes a physical memory barrier, ensuring changes are visible to all others. Reliability in multi-threaded environments depends on these architectural rules for visibility across shared memory. This is the complete JVM memory map: thread stacks for execution, a partitioned heap for shared data, and metaspace for metadata. Engineers control these territories with specific flags: -SS for stack depth, -SMs and -XMs for heap size, and -XX-max metaspace size for native limits. These rules translate directly into your daily choice of data structures and algorithms. Choosing primitive arrays over object wrappers in performance-critical paths keeps data in the fast, auto-clearing stack, avoiding the overhead of the heap. Correctly sizing an array list at initialization prevents the creation of temporary arrays in the background, which reduces the pressure on the garbage collector. Optimizing Java applications for performance requires aligning code logic with the physical realities of the JVM memory.